Welcome back, everyone. I hope you all had a nice and refreshing lunch and you're all charged up for a final post lunch session of the Qiskit Fall Fest 2025 Day 4. The session is going to be an exciting one, which is the continuation of the hands on workshop on Qiskit, where we dive deeper, explore further, and wrap up this wonderful 4-day learning journey, which is a hands on workshop journey on a high note. And we are truly delighted to have with us once again Dr. Jnana Yalla sir, CTO at DataTeach.ai, and an inspiring quantum machine learning and hybrid algorithm researcher to guide us through this continuing session. With great pleasure, I now invite Dr. Jnana Yalla sir onto the dais to continue the workshop. Please join me in welcoming him with a big round of applause.
Hello. Okay. Cool. Yes. లేదు. Okay. So yeah. Good afternoon, everyone. Okay. Good afternoon. I'm Jnana Yalla, and yes, we. So yeah. First, I will just give a gist of what we are gonna see today, so that you can just tune up your mind accordingly, and it will be kind of మరీ అంత డైరెక్ట్‌గా చెప్పకుండా ఒక ప్రాసెస్ ఇచ్చి చెప్పడానికి it will be kind of cool, right? Obviously. So yeah. First thing. So in our previous session, that is yesterday's morning one, I guess, right? So in our previous session, we have seen about some computing operations, like how we are actually measuring the qubit and how the qubit measurement will be reflected for the answer to give a particular answer. And we call it as a bond rule. Okay. So that's the one which we did. But the last concept, what I told, that is about the bond rule and stuff like that. So I kind of, rushed that particular one. So I would like to repeat that one again so that it makes sense. Like it actually makes sense. Cool. So, and also I heard some of the guys who told me exactly asking me what is bond rule, direct what is bond rule. So first, let me start with that concept and slowly we can move on. And we'll be seeing what are the states, like how we can show the states, like the bracket notations and stuff. And we can move on to gates and processings and stuff. So I have something in my mind. By the end of today, I would like to accomplish something. Let's see whether time permits and whether we are able to do that particular stuff or not. So I guess everyone have their laptops, right? Okay. Cool. So I'm just thinking, let's see how it actually goes. First, measurement. So what did I mention about measurement in our previous session? Did I say anything about measurement in my previous session or normally before or whatever? As a measurement, what is this measurement concept? What will happen in this measurement? Observing, yes. So when we observe something or when we calculate something, that comes as a measurement. Like when I say I am measuring a quantum state, I want to measure the value. I want to see the value. I want to calculate the value and observe the value. That is the entire meaning behind measuring a quantum state. And I also mentioned this one point, and that point is that when I measure a quantum state, what will happen? Exactly. It will decompose to any one of the basis state, right? So what exactly is that? So that is the entire measurements and entire bond rule. That's the same thing. Now, so we know that when I measure a quantum state, it loses its superposition nature and just falls back to one of the base state. Okay. So I can write it normally, like not an exact direct physics. I can write it like this. So I have a quantum state. And I mentioned about one thing correctly, like one thing specifically. That specific thing which I mentioned is about measurement. Okay. So I also mentioned this point, like measurement in normally we will do something, we will perform something, then only a measurement will be taken now, right? And normally to say as per the subject wise, or in order to say as per the subject wise and stuff like that, the measurement can be determined or can be defined as a Hermitian operator called A. Why? For example, I want to measure the length of this pen. So can you just look at this and say the length of this pen exactly in centimeters? If you are able to say it, you are NTR from Nanak Premoto actually. Really. But we are not that talented and there is no Sukuma here to give us the script as well. So that's why we will use something called as a scale. Okay, plastic scale or whatever. And we will keep the particular thing. So meaning, in order to find the value of an entity, you're using an instrument. Yes or no? So without an instrument, you can't find a value, right? And that instrument with respect to quantum and with respect to physics, I will call it as a some random physics operator or physics object. Some physical nature, whatever physical nature it can be. Electricity, yeah? Okay. Magnet, okay. Light, okay. What any physical quantity, okay, any physical unit can be termed as a measurement guy or a measured guy or whatever. Okay. Now, with respect to quantum, that physics operator which I'm mentioning, yeah, that physics operator which I'm mentioning right now can be defined as a Hermitian operator. Okay. So this is the one another thing. First thing, anything which can be called or which can be termed as a measurable thing can be shown in the form of a physics object. Scale is a physics one. Similarly, I can show any kind of mathematical concept or any kind of any physical nature as a measurable quantity. Okay, that is first thing. And second thing, that measurable quantity or that physics quantity which I'm taking can be defined or will be in the form of a Hermitian operator. That is the second point. Okay. First point is measurable can be shown as a physics object or physics operator, and that physics operator can be shown as a Hermitian operator. What is Hermitian? That like, do anyone remember Hermitian? Correct. What's that? Complex conjugate equal to same. So yeah, let me just move this thing. Yes, cool. So what do you mean by this complex conjugate? Very simple. First, I will create a random matrix M. There is no relation between this and the entire of what I'm talking. So just create a random matrix, random whatever matrix you want. So I'll make it like this, like A plus I, tell any alphabet. A plus I, A, B, C, D. Ah, okay. B plus I, E, F, S. Okay, whatever. I don't know alphabets, never mind. Okay, so let us consider this is a random matrix. Okay, now first thing is the conjugate. Okay, complex conjugate that is determined by star. That this guy gives me this one. Okay, that is a star symbol. This star signifies that complex conjugate. That's it. Okay, there is nothing to do with the Hermitian and this one. This star symbol defines the complex conjugate. Okay, now simple deal. Now there's one another guy called as a dagger. Now, now, so what is a dagger? Very simple. So when I say dagger, okay, dagger is like a cross. Okay, cross symbol. M dagger is can be defined as complex conjugate transpose. Okay, so if I say M dagger, what I will do? First, I have M star matrix, this one. Okay. So the complex conjugate, I will write A minus B C H. Okay. And I will simply transpose this guy. So what? I guess you guys know the transpose operator. Row become column, column become row. So it will be A minus IE, C minus IJ, B minus IF, and D minus IG. So this is known as M star. Sorry, M dagger. M dagger equal to M star the whole transpose. Star is nothing but complex conjugate, meaning you won't change the sign of the real value. So for example, what is a complex value? Complex value will look like this, yes or no? It will be in the form of A plus IB. Okay. So this is a real term and this is a complex term, right? So when I say complex conjugate, it's very simple. Real term will be the same. Okay, real term will be the same, but the complex term is there, na? That sign will be flipped. If it's plus, it will become minus. Minus and plus. So it will be A minus IB is the complex conjugate. Okay, that is the deal behind what this is what is meant by complex conjugate. And if you do the complex conjugate and then if you do the transpose, then it will give rise to dagger. Okay, straightforward deal. And what is Hermitian? Very simple. If M dagger equal to M, then we will call it as a Hermitian. Right. Hermitian matrix, Hermitian operator, Hermitian operation, whatever you just name it, not a problem. But this is the entire deal. So if the dagger value gives rise to the same value, then I will call it as a Hermitian operator. Okay, I can say a matrix M as Hermitian if M dagger gives rise to M itself. Ante ente, if I do the complex conjugate and if I do the transpose, I'll get the same value as the answer. Okay, na? That is a simple deal behind your Hermitian operator or Hermitian matrix. And the measurable which I was defining or which I was mentioning, A, the measurable operator or the observable A is always in the form of Hermitian guy. Okay, just keep that in your mind. The measurable A is always in the form of Hermitian. Okay, why it should be always be in the form of Hermitian? I will say why Hermitian is it. But that is the deal. Now, so can any one of you tell me or try what can be A? Give a random example of A. Bro, I can take A like this, Anship. So what I can take A as? Tell me any quantity, any physical object or any physical operator. What can be A as? What you want it to be? Pen. Okay, measure the. Okay, no, it's bit complicated, light. So okay, with respect to quantum, A should be a physical object. Okay, like physical object, its pen is correct, but if you wanna talk in more physics aspect, you say material. Okay, or a lattice structure. That is good answer actually. You can simply say a lattice structure. Okay, so I can say A as my laser as well. But instead of directly saying like laser, I can say A is photons. Okay, that's the real meaning behind it because we are talking about quantum, right? You need that. Okay, so A for this example, or in order to write, you can use A like this, like an electric impulse. Else you can simply be like a pulses, or electrons, or photons, or lattices, or magnets, like magnetic properties and stuff. Simply to put, all the bosons can be called as operators. So you don't need to stress that much on what are bosons and all those stuff, but that's the entire deal. Okay, the force carrying guys, simply to put, the people who are responsible for carrying the force, okay, they can be called as an operators, but you don't need to think about it that much. Now I hope you got the idea of A. What is A? What is a measurable A? Right? Everyone, what is measurable A? Now come to the real deal. I was talking about inner product the other day, right? And I told something like this. What is the meaning behind this? Okay, sorry. This, my bad. Correct. What's that? A probability of s- state changing from what to what? Good. Psi to phi. Okay, this is the probability of the state changing from psi to phi. Okay, this is Born rule. Simple thing. So if anyone asks you what is Born rule, simply say that or directly say that. You don't need to use any kind of weird language. Directly say that if or not if, like, directly say that the term or anything, any particular thing which is used to find the probability of the measurement. Okay, that is known as your, okay, my bad. Okay, so if you find the probability of the measurement, that is known as your Born rule. Okay, so normally I know, like when the YDSA happened in the 1800s or something like that, they know. Okay, so if I observe a particle, it will lose its nature and shape. They know about it, not a problem. But um, after it losing its nature, where it's falling? Is it falling to particle state or is it falling to wave state? Is it falling to zero or is it falling to one? It definitely falls to any one of the guy. But at what probability it is falling to any one of the state? That is defined by Born. Okay, the probability measurement. So the probability measurement first time came into play because of Born rule only. Okay. So simply to put, when I defined this, I said alpha square equal to prob of state being in falling into zero. Remember, alpha square is the probability of the state falling into zero after I measure it. That's the thing which I told. This thing was not there before. Bond rule came into play, and that's why this guy came into play. Really, the alpha here, this alpha here is nothing but this one, zero, right? I can say some random value. Okay, I can say like this. This is the meaning behind this alpha. This alpha is this one actually. Okay, but if anyone wants to give an introduction and stuff like that, they simply be like alpha naught plus beta 1, alpha square is a probability. They will directly say like that. But the real deal is this one. Okay, 0 of psi. Yeah, correct. Okay, that's the simple deal. And this defines what, for example, if I make a square of it, that defines the probability of psi falling to 0. Okay, simple. Psi changing to 0. That's it. Now, in order to expand this in a formula point of view or something like that, we can simply go like this actually. Meaning, we can consider in this way. For example, so till now we have talked about only two states, 0, 1. Okay. But in reality, there will be n states. 0, 1 matrame undadu. There can be n states anamata. So that's why I will just draw this one or I will just write this one. So I can write an n state in this way. See. And yeah, one more thing, the amplitudes are there, not the coefficients. Need not to be only alpha, only beta. You can give whatever letter you want, not a problem. Okay, until or unless the max is correct, you can use whatever letter you want. Okay, so yeah, I'll just use alpha 1, beta 1 like that. If you want, you can use whatever you want, not a problem. So I'll make alpha 1 of zeroth state plus alpha 2 of first state plus so on up to alpha n of n minus 1 state. Make sense? Is it making sense to anyone? So what is this exactly? Making sense, right? What is it? Come on, right? Anyone? Okay. N-dimensional state. Or I can not n-dimensional. N-state vector. Okay. A quantum which is having an n states. Normally, if I say alpha naught beta 1, it's nothing but a quantum which is in two states only. This is with respect to n states. That's a simple deal. Now, can I define this in this format? Can I define this in this format? Yes or no? Okay, so I simply define it like this. Okay, very simple. Just a simple mathematical notation. Something can say like continuous sum of the amplitude plus the state. That's it. Okay, direct mathematics, direct implication of mathematics. I'm not even doing anything now. Okay, so yeah, I have 5 on the. So when we are doing an actual measurement with operator A, now I can write it in the form like this. So this is a state, right? So when I measure this state with operator A, the official definition goes like this state is there na, that falls to any one of the eigenstate of my A. Okay, that's the by default definition or a bookish definition or textbook definition. When I measure a quantum state of n dimensions, or sorry, n states, n basis, okay, with an operator called A, then what will happen simply, this quantum state will project, or I can say decompose to one of the eigenstate of A. Okay, one of the eigenstate of A. There's a simple deal. What is an eigenstate? If I write like this, yeah. So if I write like for any I, this is the eigenstate. Okay, simply to put, that is the eigenstate. And this is the relate or the respect to eigenvalue, which defines the amplitude. Okay, which simply defines the amplitude. Nothing. You don't need to think about anything. Directly to say, and the real physics definition is not amplitude, but simply to consider, we can consider it like an amplitude. Okay, just consider it like an amplitude or consider it like a coefficient of the particular state. That's it. Now, when I am doing A on site, I can write like this actually. I can write like, I'll be writing like this. Okay. So what are you observing here in this particular case? What is the change? Okay, don't consider this one. This is completely all right. What is another change? Can anyone figure it out? Can anyone see it? What is the change? What is happening here? What is the difference? Here it was before I minus 1 state, and now it became AI state. Why? Can anyone answer why it became AI state? I can keep like I minus 1 only, right? So why AI? Okay, no, you can't see. Okay, complete. Okay, now it came up. Okay, fine. Now say it. I minus 1 state became AI state. How and why? How light? Why? Can you just relate it with the definition which I gave for the projection or for the measurement? So what is the definition I gave for the measurement? It will be projected into one of the eigenstates of operator. So what I mentioned about eigenstates, AI is the eigenstate. So what do you mean by projection? Ante very simple. Normally psi is there, not the actual quantum state. The actual quantum state resides in I minus 1 state for a particular I. If I equal to 1, it resides in 0th state. If I equal to 2, it resides in 1th state. Okay. Now, when I actually measure it, when I'm actually measuring it with the operator, okay. So when I'm actually measuring it with the operator A, what will happen? I told. So this will be projected in the sense like, however, it will be just deviating or it will be just going into one of the state where A's eigenstate is there. Okay. So from the 0th state, it will move to some AI. That is a simple deal behind it. It will simply project there until it will simply go there and uncount. Okay, for example, if you're sitting, you're having 2 rooms, okay, and the outside temperature is 30 degrees Celsius. One room has AC, let us consider, and you're sitting in the hall. When a temperature increases, what will you do? You sit there only, yeah? If you have a chance, definitely we will rush into the AC room, right? So when something is changing, you are moving on to another place, right? Similarly, a quantum state will be just like that. Normal, undisturbed, stable, atla untadi. But when you are in disturbing it with a measurement operator called A, it will be unstable and it will try to move on to one another state. And that one another state, luckily, it is nothing but one of the eigenstate of A. Got it? Simply to put, when the temperature increases as you are going to an AC room, what will happen? Ante, a normal quantum state, when you are giving a measurement operator or whenever observing this thing, move to one of the states. That one of the state is nothing but the eigenstate of A. Got it? It will just simply change the positions. That's why this I minus 1 becomes AI. Okay? Because it will be in a superposition state code, obviously. It can't be a single value. It will be in a superposition state. Now, phi is what? Output. Output state vector. Input is psi. Okay? Under the initial state is psi. And after a measurement, it became phi. Okay? That's why for the initial state, it is I minus 1, stable, normal, just like that, no change. But when you're measuring it, it will be moving on to one another state that is nothing but the eigenstate of A. Simple deal. Close. Now, I have this. I have an output vector, which is in a superposition state. I want to find the probability of the actual measurable output, the actual value to be um, A5, let us consider. Okay. So AI means I can be anything, like I can be up to n, whatever. Why? Because we have n states, kabatti I can be n. Now, when I say what is the probability of the output being A5, because this is in a the output vector is in a superposition state, right? As the output vector is in a superposition state, I have the values with respect to everything. Now, if I want to find the probability of the actual output being A5, then what I will be doing? Let us go with the actual thing again. C1, A1, C2, A2. Let us consider something like this. What is the probability of the output being A1? C1 square, correct. It is C1 square, right? Why I can write it like this now? Yes or no? Can I write it in a form like this? Can I represent it like this? So that's a simple deal actually. Now, similarly, when I take this phi, which is of Ci and Ai, I can say that the probability of the output being A phi can be written like C phi square. Yes or no? Adhamainda? So it can be written like C phi square. Now, by using bond rule, I can write C phi as this thing. Okay? That's a simple deal behind the entire bond rule, probability, everything is the same deal. Okay? Just like that. Simple stuff. So this is the entire deal of your actual measurement. So this is why when you measure a superposition state, it will decompose to any one of the value. Okay. So this is how you can officially, what can I say, display it or demonstrate it or show it. Okay. So if anyone asks you, like you take alpha naught plus beta 1 and you say alpha square is a probability of 0. How? This is the entire reason. So this is the how behind why alpha square is a probability and alpha is the amplitude. Okay. Got it, everyone? So why? Because inner product gives the amplitude. It is a complex scalar, which I already explained in the previous session. The square of it will be a value and that value is a probability. Okay, na? Got it? Simple stuff. Now, this is the entire deal behind the basic sensor. Now, now let's go to something called as Bloch sphere. The next topic. So, in the previous sessions and stuff like that, the speakers were mentioning about displaying the qubit and they use some sphere kind of structure. Okay. So that sphere kind of structure is called as a Bloch sphere created by a guy called Felix Bloch. Okay, I don't know which year. I think 46, I guess. I forgot. But it's created by that guy, not 46 Pro, but something like. But he is known as Felix Bloch, and that guy created this Bloch sphere. Now, why we use Bloch sphere? Very simple. In order to see the state of a vector, sorry, state of a quantum guy. Or simply to put, in order to visually represent the quantum state, I use something called as a Bloch sphere. Okay, that's the direct definition behind it. Okay, simple. Why I use Bloch sphere or what is a Bloch sphere? Simply to put, visual representation of, I can say, qubit. A visual representation of a, and here just add one word, that is single qubit. Okay, the visual representation of only a single qubit is done by using Bloch sphere. Only a single one. It's not multiple qubits. For example, if I'm having two qubits I cannot show in a single Bloch sphere. In order to represent two qubits, I need two Bloch spheres. Okay, a single qubit can be defined, can be represented by using a Bloch sphere. Sorry, now I'm a very bad artist, but let me just try something. So technically, the Bloch sphere will look something like this. Okay, and these are the axes actually, and there will be a circle around it which I can't keep, or let me just try. Don't judge. Okay, wow. So some random circle, okay? It's not a circle actually, it's a sphere. Why? Because it's in three dimensions, okay? And what happens is that the vertical axis is your z axis, okay? Don't confuse it with y and coordinate systems, okay? The vertical axis is your z axis, and the horizontal guy is your y axis. And the guy who is poking out from the screen, he is my x axis. Okay, and the zeroth state is there na, zeroth state, zeroth state resides on the north pole. So what is north pole here? This guy, that is my north pole. Okay, so here I will have my zeroth state. Okay, and state 1 is in my south pole. So south pole is this one. So here I will be having state 1. Okay, simple deal. Okay, that's how a Bloch sphere is. Now, how exactly I can define a state inside a Bloch sphere? So I told you psi equal to alpha naught plus beta 1. How can I show this inside a Bloch sphere? So how can I show alpha naught plus beta 1 inside a Bloch sphere? That's the entire deal actually. Simple. For that you need to know one equation of Bloch sphere. That equation goes like this. I will also tell the derivation of how that came, not a problem. But yeah. And after this, I will directly go to gates and rotations. So follow on from here itself. Else you will not get what you mean by rotation gates or what is poly, why poly, so you can't get them. So that's why understand from here itself. Okay now? Now, the Bloch sphere equation goes like this. I can show as quantum state psi as this one. Cos theta by 2 O plus E you can use any value, okay? You can use phi, but don't use gamma. Phi sine theta by 2, 1. Okay? This is the actual deal behind it. So this is how it looks like. And this is how a Bloch sphere thingy looks like. Okay? How it came? Very simple, very straightforward, very easy. Legit very easy. Okay? Don't even think that much. Simple. For this, I can write like this in the first place. Yes or no? Okay? This is in a Hilbert space or something. You can just consider any random space. What is the space of spherical thing called as? If you're having a spherical space, what is that called as? Correct. spherical one. We'll call it as a polar coordinates antam. Guttunda? So a spherical in a spherical space, the values are or the values can be defined as a polar coordinates. Meaning simple. For example, in a coordinate space, if I have x and y, okay, in spherical space, I can simply write them like some random. So you can use any values. Okay, you just use any variables you wish. It's not like you should use the same values. I can write like them in polar coordinates. And I can simply be like R0 and R1 is greater than or equal to 0. Okay? Simple polar coordinate mathematics. There's nothing deep here. Just a simple conversion. If you can't remember this or if you can't bring that back to memory, just keep this one thing in your mind. Okay, not that deep or not that complex or anything. Just a straightforward stuff. Deal is the coordinate system, guys, can be defined in polar coordinates like this. Okay, na? Very easy. R ఏంటి ఇక్కడ? Some random value. ఏడొకటి. Okay, you don't need to think about it that much at this point of time. So picture light. Now, so in this case, yeah, okay, cool. So in this case, what I will be doing is that I can show it in the form like this actually. So when I have alpha naught plus beta 1 equal to 0. Oh, sorry, equal to some random psi. Now, and one more rule goes like this: alpha square plus beta square equal to 1. Okay, just keep these two things in mind in two different hemispheres or whatever. Now, I can show my alpha in this way. This is gamma actually. Okay, and I can show my beta in this way. Okay, and yeah, look, this is not R, this is gamma. This is gamma. This one. Like you will be having gamma like this, right? Remember? Something like this will be there in radioactivity, that one, actually. Not R. Don't confuse that with R. Okay, I can show like this. Cool. Now, one more thing. Why, and I can show it in one more way also. How and why am I able to show it in one more way without any constraints? Ante, I will explain it right. When you are dealing with a Bloch sphere or when you're dealing with the spherical coordinates of quantum, okay, in that Hilbert space kind of thingy, very simple deal is you'll be having something known as global phase. Okay, you'll be having something known as a global phase, which is defined by simple lambda. No knots, no ones, no g's, nothing, just a direct lambda. This guy is known as a global phase. Okay, first of all, what is a phase and what is theta? I will explain that. But for now, just remember this: there will be something called as a global phase. And what is global phase? Ante, it doesn't do anything. It don't have any work itself. Okay, it simply exists just like that. Okay, why I am saying like this? And very simple. For example, if I take, let us consider I'm taking a random value. Okay, random value called a, and let us consider this a is in a polar coordinate. Okay, meaning it's in a spherical system. When a is in a spherical system, when I'm applying anything, it should change kada obviously. I will give you a value 5 into something unknown. So except 1 and 0, like except 1, if there is anything, then obviously it will change. Yes or no? I will give any random value, obviously it will change. Except 1, because 1 is an identity, right? Now, if there is a polar coordinate called A, okay, and I'm multiplying it with some value, then it should be something different than A, yes or no? At least minus A and kuda different kinda lekka, right? So at least it should be kinda different from the original A after I multiply it. But the deal goes like this. When I actually multiply A with a global phase, okay, when I'm multiplying the A coordinate which is in a polar system with a global phase, it won't change. Okay, so asal ఏముండదు. So even in value, even in state, even in anything, it won't change. Both are same only. Okay. So and that's the reason this guy is considered as he don't have any work. He simply exists just like that. Okay. That is called as a global phase. Now, why this global phase is important is, let us consider it is like that now. Now, if I go like, I can write in this way also, right? Yes or no? Can I write like this also in global phase? Why? Because anyway, it's not making any change. Anyway, this guy, I mean, this entire term is not making any change. So I can write some random stuff here. It won't be a problem. Why? Because anyway, it will not change now. Are you getting the point? So anyway, if it is not changing, I can use some random stuff there. I can keep an entire God equation out there, but still the output will be A only. Why? Because nothing changes. If you're applying something inside a global phase, or if you're applying something within or like a global phase, nothing changes. So that's the reason whatever stuff you apply, not a problem. The output is still the same thing. Okay, that's an important deal. Why? Because using this property, we will define the entire block sphere. Now what I can do under, because of this phenomenon, where I can do anything in the global phase, but it will not affect my output. What I can do, I can simply write this guy as something like this. What I'll make alpha naught as 0, sorry, gamma naught as 0, that is this term, gamma naught r, which, so let me just change this guy to, okay, gamma naught as 0, and I will make some random gamma 1 as 5. Okay, anyway, it's not making any change, right? So I can just use any of the random values which I want. Okay, so now how I can write alpha as something like r naught in r naught plus, oh sorry, alpha as r naught and beta as r1 e to the power of minus I 5. Right? I have these values at this point of time. Now, one more thing. What is alpha square plus beta square? 1. Trigonometric identity mein, I can make this right. In trigonometric identity, sin square theta plus cos square theta equal to 1. Can I represent it like alpha square plus beta square equal to 1? Yes or no? I can do that stuff. Both are technically the same. Are you guys getting the point? So as both are technically the same, I can make alpha square plus beta square equal to 1. Okay. Now, what I can write here as, so why I'm looking back is like in my screen, it is actually very small. So that's why I'm actually seeing is it really very small or not. Okay. Now alpha square plus beta square, I will write as 1. Okay. Sin square theta plus cos square theta equal to 1. So I can simply be like r naught equal to cos theta and r1 equal to sin theta. Yes or no? Why? This guy will not make any change. Are you guys getting the point? The global phase will not make any change. So I can keep any random stuff out there. So it will not be a problem. Now I can write my alpha as cos theta and beta as what? Sin theta. Okay. So I can write it like this. I can write beta as e to the power of minus I phi of, so I can write it like sin theta. Okay. Now let's go back to the original qubit equation, original block sphere equation, or original qubit equation. What is that? Alpha naught plus beta 1. Place of alpha, keep cos theta. I can write my psi as cos theta naught plus e to the power of minus I phi sin theta 1. But wait, when I define the block sphere equation, but wait and don't wait, write this. This is a step only. But I am saying like don't conclude. Okay, just wait. Why? Because when I wrote the block sphere equation, I wrote cos theta by 2. I did not write cos theta. Remember? When I wrote the actual block sphere equation, I was like cos theta by 2 0 plus e to the power of minus I phi sin theta by 2 of 1. Why that by 2 came? So normally it's like this. It's clean. So max, everything is, every mathematical is good, doing good. The phi phase is good. The global phase is good. Everything are cool. Why theta by 2 in place of theta? Very simple deal. Okay, very straightforward, very simple. But I just want you to keep your visualization stuff. Why? Because it is actually useful at this point of simple. And your trigonometric ideas as well. Now I will explain two things, phi value and theta value. These are variables only. These are not like you can keep whatever you want. These are the same stuff. You keep the exact stuff. Okay. The random all things I was like you can keep whatever you want, right? But this is not like that. You should definitely keep these values only. Why? Because simple. Let us go back to the block sphere again. This is the watch state Y. This is which is poking outside is X. And the guy on the top is my Z. Okay. This is how it is. Now, simple case. So this is where my 0 resides and this is where my 1 resides, right? What is theta? Theta is this one. This is theta, meaning visualize a sphere. This is a sphere, okay? Consider it is a sphere. Now, if you rotate in this way, okay, that is theta value, meaning it will rotate in the z-axis only, like this, okay? So that's why theta value belongs to, that's it, okay? It belongs to 0 to pi only. Why? Because initially 0 to state is here, z1, and theta is this one actually. Okay, it defines this movement only. So that is your theta. Now, phi. Phi value is this guy, this rotation. This angle is phi. Okay, so meaning the rotation in the xy axis towards your side. Now let us visualize the same sphere. So this is my z. Okay, I will just bring my z somewhere here. Now if I rotate it like this, like a top, then it is your phi. Okay, that angle is your phi. So now tell me what can be the range of phi? Theta value is from 0 to pi. Okay, now when I say phi, it is this rotation. Rotation of your on top of your xy axis, this rotation. So what can be the range of phi? Exactly. What is that again? 0 to 2 pi. So phi can be from 0 to 2 pi. Okay. So that is the entire deal behind it. So this is your theta value and this is your phi value, which is very important, legit very important. Entire quantum computing, if you want to be a quantum guy, very important. You forget this, gone. Really legit gone. So this is actually very important. Okay. Important stuff, which you definitely need to remember so much. Okay. If they ask you theta, so first thing is the Bloch sphere guy, very important. This is Z, this is Y, and the guy who's poking you is X. Okay. And theta is this action, the rotation of your Z axis within you from your Z axis, not off Z axis, from your Z axis. And phi is this angle rotating on top of your XY plane. Okay, that is your phi. It will be of complete circle, 2 pi will be there. But your, what is this guy? Theta is only pi, 180 degrees. Okay, that's a simple deal you need to remember. Now, by using this, we found that it is not theta but theta by 2. Why? See here. If I want my side to be 0, okay, let us take the equation. Okay, let us take the equation which we have built till now. Let us take the equation which we have built till now at this point of time. Till this point of time, we have built something like this. Yes or no? Like we have made cos theta of 0 plus e to power of minus I phi sine theta of 1. So this is the guy which we have built till now, right? Now, if I want my psi to be 0, then what should be there? This guy should be 1 and this guy should be 0. Yes or no? If cos theta is 1 and sin theta is 0, then the output is 0. Now look at the Bloch sphere on the your right. Here, if the value should be in zeroth state, if the value should be in zeroth state, what is the theta value and what is the phi value? Can anyone tell me? If the value should be in zeroth state, what is the theta value and what is the phi value? Correct. Theta value is 0 and phi value is, it can be anything. Okay. Phi value can be anything, not a problem. It's not necessarily 0. Make theta as 0 and keep phi whatever it is. So theta is 0, keep phi whatever it is. It will just rotate like this only. It is in a 0 state only, not a problem. Okay. So I will simply make theta as 0. Okay. And phi is phi, random phi. If theta is 0, cos 0, 0 plus e to power of minus I phi sine 0 of 1. Satisfying or not satisfying? What is cos 0? 1 only. So it is 1 of 0 plus 0. So our answer is 0. It is satisfying. Cool. It's cool. Now let's go to the one state. So if you are going to one state, then what should be your theta value in one for one state? What is the theta value? Not 90. Sorry? I think I heard somewhere correct. Theta should be pi. Now, I will draw the Bloch sphere again here. So y, z, x. This is theta. This is the count of theta. Now this is 0 and this is 1. So now if I want my vector to be in one state, I want my vector to be in one state. What should be my theta value? Pi. Yes. So when theta is 0, it is in the zth state only. That is a 0th state only. Where my 1th state is here. So I want to rotate it pi radians, meaning 180 degrees. So if I rotate it 180 and 0 will be will be coming to hello. Yeah, okay. 0 will be coming to your 1. So theta should be pi. What is the phi value? It can be anything, not a problem. Try to implement this. Sorry. Yeah. Try to implement this in the formula right now. What is cos pi? Forgot. -1. What is sin pi? 0. Good. Implement it. What will be? It will be -1 of 0th state plus 0 of, e to the power of minus unterlagane 1th state. So the output is -0. Is it satisfying? Is it satisfying? The output should be what? Really, at these angles, for these angles, my quantum state should give an output of 1, right? So the quantum state is here. So it should give the output of 1. But for these angles, if I apply these angles into the formula, so I'm getting the output as -0, meaning 0 in the negative phase. So it is not correct. It is wrong, right? Now, come back to the actual point. The deal goes like this. If theta is 0 and phi is phi, the output should be 0. Meaning cos theta should give me 1 and sin theta should give me 0. Okay? Cool. Completely alright. Now, if my theta is pi and phi is any value, not a problem. The output should be what? 1. Yes, the output should be 1. So in that case, my cos theta should be 0 and sin theta should be 1. But here it is not satisfying. So for that, what we need to do? Try to do by 2 on both cases. So if you do cos theta by 2, sin theta by 2 here, the output will not change. 0 by 2 is 0 only. So it is 1 only. And anyway, sin 0 is 0. So 1 only, not a problem. So it is not changing. Now try to implement on this side as well. So if you try to implement this on the other side, that is for the 1th state. Now what is happening? Let's try to execute theta by 2. What is pi by 2? 90 degrees. So cos 90, how much? What is cos 90? 0. What is sin 90? 1. Is it satisfying? Now it is giving me the output as 1. So that's the reason we use theta by 2 instead of theta. So that's how your what can I say? Your quantum state takes the form of cos theta by 2 of 0 plus e to the power of minus I phi sine theta by 2 of 1. So that's how this guy came into play. Did you guys get it? Did you guys keep the entire step-by-step thing in your notebooks and stuff? Because only if you keep like that, then only when you revise, it will be, accessible, or you can just brush it up. Else, you can't just remember it just like that. Okay? So right now, also at this point of time, also I'm not so sure and I'm not so confident that you get every step directly. But you just need to see that thing again. If you see that book again, then you'll be getting it. Okay, that's the main deal actually. That's how this thing works. But yeah, did you get the gist of how it actually happened? Like, did you get a gist of how actually you got this value, the psi value, and how exactly this Bloch square equation came into play? I hope everyone got it, right? Yes or no? Okay, something like that. Now, so this is how your block thing came into play, and this is your entire block sphere, and this is the entire condition case of your block. Okay. Now let's go to something called as rotations. Understood block sphere, right? The theta, phi, everything. Now let's go to rotation. So what do you mean by rotation? Simple stuff. The thing which I mentioned right now as theta and phi I mentioned, that only is rotations. Okay. So if I implement the theta with a particular angle and phi with a particular angle, they are called my rotations. That's it. Simple deal. Okay. Now visualizing the block sphere again. So this is the y-axis, z-axis, x-axis. Now, so if I say rotation around z-axis, okay, the word called as rotation around z-axis. The meaning is I am rotating it in this way. Okay, that's the meaning behind it. So I am rotating it like this. For example, simply to put, if okay, I don't know how to show it to you people. Okay, both are same. For example, this is okay, this is the state. Now some- yeah, something. Hello. Okay. Hello. Hello. Okay. So let's try how it actually goes. Now, so for example, if I take my qubit, this is the zeroth state. Okay. So from the zeroth state, let us consider some random state here. It is like this, inclined, not on this particular zero. So if I say that I am rotating it around the z-axis, the meaning goes like I am rotating it in this way actually. Okay. So meaning I am rotating it with respect to phi. So when I rotate the qubit state or when I rotate the quantum state with respect to phi, అంటే phi angle తో నేను rotate చేస్తే that is rotation around z axis. Okay. So when I say okay. So when I say rotation around z axis, so when I say rotation around z axis, I'm simply just rotating it with respect to phi. That's it. Okay. Straightforward thing which you need to remember. Rotating it around z axis. Rotating it 20 degrees around the z-axis. What is the meaning? Phi equal to 20, correct word. We should exactly define it like that. Simply, I'm rotating the qubit with phi equal to 20 degrees. That's it. Okay, na? So that is the entire meaning behind it. Rotation around the z-axis, ante this is the meaning behind it. Okay? Now, Rotation around x-axis. What does that means? X-axis there na? Itla. Okay, meaning rotation around x-axis is nothing but theta equal to. Okay, meaning same. Z is there. Yeah, I can rotate Z. So this is how the Z looks like. Okay. Now I am rotating it with respect to rotating it around x-axis for 45 degrees. The meaning goes like this actually. This is how the rotation happens. Okay. Meaning I am making theta equal to 45. That's the simple deal. Z equal to 0. Sorry, not Z. Quantum state is in 0th state. Okay, meaning north pole directly. And I'm rotating it around x-axis with uh, angle of 45 degrees. Angle of 45 degrees rotating around x-axis. Very simple. Just make theta equal to 45. Answer. Okay, that is your rotation around x-axis. When I say rotation around z-axis, it is phi. Rotating 10 degrees around z-axis, phi equal to 10. Rotating 20 degrees around z-axis, phi equal to 20. If I say rotation around x-axis, it is theta equal to. Okay, meaning this guy, this one. So if I say rotation around x-axis with angle of 45 degrees, the simple meaning goes like theta equal to 45. So if I make theta equal to 45 degrees, the meaning is I am rotating the qubit state or rotating the quantum state with respect to x-axis, rotating it around the x-axis with 45 degrees. That is the entire meaning behind it. Got it? Simple deal. Just try to visualize. That's why I was like visualize. Okay? Only if you visualize, you are able to do it in a very clear manner. Rotating it around the x-axis meaning is theta equal to the angle. Now, actually, y-axis is not that much to consider. You don't need to consider y-axis rotations that much. But anyway, to say it, it is this thing. It rotates in this way actually, in towards your side. Meaning it will rotate in like this. Meaning, for example, this is z. Okay. So if I say I am rotating it, rotating y with respect to pi. No. 45 degrees only, that is concerned. I am rotating my qubit state or rotating my quantum state around the y-axis with an angle of 45 degrees. Meaning goes like this. That's it. Okay, this is your rotation around y-axis. This one. Okay, so if I say rotating my quantum state with angle of 45 degrees around y-axis, simple, just rotate it in this way. 45 degrees, so 90 degrees. 90 degrees over. Okay, that is the entire deal behind it. Done? Got it? So that is a rotation around y-axis. And for y-axis, there is no proper theta or phi values or something like that. So if I say rotation around z-axis, I have phi. If I say rotation around x-axis, I have theta. But for y-axis, there is nothing like that. That's why it is not that required actually. So for the beginning stage, like for the beginners or for the friendly manner, so y-axis we won't consider it that much. Okay, if you're going to advanced application, then we will be having ry, rotation around y, because rotation around y do both the phase as well as beta also. So that's something which I will be explaining it slowly, but as the entire deal. But x and z has a direct implementation. So that's why it is of for the beginner friendly thingy for the something like up to 1 month of your quantum journey, you won't be having x-axis and y-axis rotations. Okay, sorry, x-axis and z-axis rotations. That's it. After 1 month is done, when you're exploring the official quantum algorithms, quantum circuits, and stuff like that, there you can use your y thingy. Okay. In order to understand your y, you should know x and z in a very great manner. Then only you can understand y. That also I will explain how one should, because y can be determined as a linear combination of x and z actually. I'll show that. Now, so as you already understood the rotations, let us start with the rotation gates first. Okay, first let's start with the gates actually. Did you guys understand what you mean by rotations? How rotations will happen? Okay, so how rotations actually happen? Rotation around x-axis అంటే ఏంటి? అన్ని తిరిగేదే. Theta value. Yes, correct. Rotation around z-axis is 5 value. That's it. Now, let us go with the gates official. From here, you need to listen way more carefully because actual quantum computing starts from here. The quantum computing starts from here only. Okay. Now, what are gates? Normally, gates ante enti? Electricity lo, computers lo, gates. What are gates? Why we require gates? What are gates? Simple, just like this. Just say what do you mean by gates casually. Some XYZ operation. Yes or no? ఏదో ఒక ఆపరేషన్ చేస్తాం. ప్లస్ మైనస్ ఏదో ఒకటి చేస్తాం. అండ్ నాండ్ ఆర్ నాట్ ఆల్ ఆర్ గేట్స్. వై గేట్స్ ఆర్ వాట్ ఆర్ గేట్స్? సింప్లీ టు పుట్ ర్యాండమ్ ఆపరేషన్. ఏదో ఒక ఆపరేషన్. ఇఫ్ ఐ డూ ఎనీ ర్యాండమ్ ఆపరేషన్, ఫర్ డూయింగ్ దట్ ర్యాండమ్ ఆపరేషన్ ఐ విల్ బి యూసింగ్ గేట్స్. Yes or no? So meaning gates are nothing but any operation, an instrument or a device or something, an entity or a connections or whatever stuff which deals with performing certain operations. They are my gates. Okay. So if I want to perform, for example, if I want to find the, okay, I don't want to use any Boolean language, but if I want to find the truth value for both of them, like if both are true, then only I want the true. For that, I use AND gate. Okay. If I want to choose any one of the guys, okay, for that I'll be using OR gate. So it's something like that. For a particular operation, I'll be using any particular gate. So I guess it is better to have a break for something like 5 minutes before actual going to gates. What do you say? Yes, sir. Stored intuitions. Okay. So let us have some break for 5 minutes. Just 5 minutes, and then we can start with the actual case. In the meantime, revise that rotations and block spin and stuff. Okay. Thank you.
Dear participants, hope you had a refreshing break and some fresh air. I request you all to get back to your seats to resume our hands-on workshop session. All of you, whoever is still taking break, please get back to your seats.
Hello. Hello, hello. Okay. Okay. So let's just wait for this guy to show up. Okay. So in order to simply revise, before I just said about the block sphere and like how we can visualize the block sphere, that guy. And I also said what is the derivation in a step-by-step manner for the block sphere. Completely cool. And also I mentioned about what rotations. Yes, we talked about rotations, like how actually the rotations will happen and all those stuff. Okay. So now we can actually go to the official operations. They are my gates of quantum. Meaning, first, what do you mean by gates? What are gates? That's what we show. Any operation, any random operation which you're doing by using bits or by using anything, okay, boolean, whatever values. So any random operation, what you're doing comes under my gates. Gates are the, what can I say? Gates are the reason for uh, operations. Okay. Now, if what are quantum gates then? What are quantum gates? Gates are any random operations. Quantum gates are any random quantum operations. So if you're doing any random quantum operations, they comes under quantum gates. Okay. Now comes the real logic or the core behind it. The simple deal goes like this. For example, if you're taking a gate, a classical gate, which is known as logical gates. When you take logical gates, this is completely based on Boolean algebra. Remember, mathematical induction on a chapter ఉంటుంది 12th grade. Remember? So the mathematical induction chapter is completely based on this Boolean algebra. Conjunction, disjunction, bijunction, everything will be there. Okay? So this logical gate is completely based on Boolean. Now, if you take quantum gates, it is completely based on only one thing, that is your linear algebra. Okay? So what comes under linear algebra? What is there inside linear algebra? What comes under linear algebra? matrix operations. So it completely based on matrices. Only matrices. Okay. So if you are having the quantum gates, okay, for example, I am having three quantum gates. I want to see what's the output. Simple matrices. Simple matrix operation gives me the outputs of the quantum gates. Okay. So that is my quantum gate operations. All the quantum gates are operated, meaning the entire quantum mechanics is operated by using linear algebra. That is by using matrices. Okay, a simple straightforward one. Now, so now if you can relate to this, I also mentioned one point when I was explaining about qubits and quantum states. What is the point I mentioned? When you take a random variable a equal to 23, this is value, right? But when you take a quantum state, it is what? It is a vector. When I take a quantum state, so if I define a quantum state psi, it is nothing but a vector. Okay. And if you see matrices are nothing but combination of vectors. Yes or no? Matrices is nothing but combination of vectors. I can say combo of vectors. That is the simple deal behind it. Okay. And that is why we require only linear algebra to find the matrices. Matrices I want to find, like, sorry, not matrices, quantum states. I want to find or I want to calculate the final state of the quantum. Use linear algebra, matrix operations, done. Now, now let us actually go to the zeroth state, one state, how it actually looks. First thing, this guy is there, na? This one. This is known as ket notation. Okay, this guy is known as ket notation. Simply to consider, to put it in mind, nothing but columns. Okay, simply to consider what is ket notation, columns. That's it, nothing else. Simply to consider columns. And this is known as bra notation, which is nothing but rows. Okay, very simple stuff, straightforward stuff. That's why we will call it as a bracket notation. That's why we simply call it like a bracket notation. Okay, now this mostly will deal with only ket notations for the beginner friendly level. And if you're going to density matrices and those operations, there only your bra notation comes into play. Okay, but for now we only require ket notations only. Zeroth state. I was writing 0, alpha 1, 0, every 0, 0, right? Zeroth state is defined like this. This is my zeroth state. Okay, and 1th state is defined like this. Okay, understood? Simple deals. These are the simple deals. Just keep this in your mind. Big basics, starting points. After this, we will move on. Okay, but this is the starting point. So bracket notation. Okay, ket notation is nothing but the columns. This is 0 vector. This is 1 vector. Okay, everything is a vector. That is the thing simply to put. Now let's actually directly go to gates. First thing is your X gate, something known as an X gate, which is also known as poly X gate. So how I can write the poly X gate as? So I can simply be like poly X gate. I can also call it as an X gate itself. Okay. I can define it in this way. So when I say poly X gate, I will should be writing like this. Okay. Sigma X. This sigma defines poly. Just simply consider like that. Okay. Really it's not, but it's consider like that. If I say poly Y gate, simply be like sigma Y. Poly Y gate. Okay. So that sigma defines poly and anukondi. Real definition card. Just consider like that. Now, notation wise, like symbolic wise, I will define like this. plus and a circle. Okay, if I keep plus and a circle, that is a symbol for X matrix, X gate. Okay, plus and a circle, X gate. The X gate matrix looks like this. Okay, what is the meaning behind it? Very simple. First, what is identity matrix? How an identity matrix looks like? 1 0 0 1. Some x into I, some random x gate kaado, some random x into I gives me x only, right? So is there any relation which you're seeing from this guy and this guy? So what is that? It's nothing but like I am reversing them, right? So meaning is simple. Zeroth state is there now. For zeroth state, if I apply x gate, the output is 1. Okay, దీన్ని మనం ఏమంటాం అంటే we will call this as bit flip operation. Okay, so what is this bit అంటే simple, this guy. The base states are there నా zeroth state, 1th state, ఆ స్టేట్స్ ఉన్నాయి చూసారా, దాన్ని మనం బిట్స్ అంటాం అనమాట. బిట్ ఫ్లిప్ కి మీనింగ్ ఏంటి? 0 will convert to 1 or 1 will convert to 0. So if I do x gate on 1, the output is what? If I do x gate on 1, the output is 0. Yes. If you want to verify, do this. And one more thing, if I want to mathematically write, or if I want to symbolically write, meaning goes like this. For example, casually, if I say like A into B, what you will be doing? This is the thing which you will be doing, right? If I say I am applying X gate on 0th state, I should not write like this. No. If I am saying like if I want to apply X gate on 0th state, the meaning, the notation should be like this actually. Okay. So if I want to apply X gate on 0th state, the notation should be like X gate on 0th state. So if you want to practically do this, first you need to find 0th state and then you need to do X. Okay, na? Understood? So you should go from right to left, not from left to right. First, you need to do 0th state. You should find the 0th state, that is the rightmost state, and then you should go on doing this thing. For example, if I let us consider random gates. These are not actual gates, randomized variables. Some X the state. If this is an operation, you should not do like A into B into C into D into X. No, this is not the way. Instead, what you should be doing? First, you should find the X the state. Do D into X. There will be an output. And then do C into that output. And then B into that. And then A into that. Advainda, you should do it from right to left, not from left to right, like our casual multiplication. Simply to put 2 into 3 into 5 into 6. 2 3s are 6, 5s are 30, 36 are 360 approximately. Let us consider. Okay. But really, you should not go like this when you're dealing with this guy. Instead, you should go like 6, 6 5 is 30. So you should be like this. And then like this. And then like this. Okay. So you should go in this manner. Okay. Ante meer ekkడి నుంచి వెళ్ళాలి? Left to right to left వెళ్ళాలి. Okay na? Not from here. That's a basic deal which you need to remember. Now, coming back. So that is your X gate. It will do something called as a bit flip operation. 0 will be 1, 1 will be 0. Quantum version of NOT gate. Okay. So X gate is nothing but what? Quantum version of NOT gate. So we have something called as NOT gate in logic operations, right? So దాని యొక్క quantumized version మన X gate అన్నమాట. Second, what you need to see is Z gate, which we will call it as poly Z. Okay, poly Z matrix Z gate. So what will this Z gate will do ante? He will perform something called as phase flip. Okay, what is that phase flip? It's 1 0 0 minus 1. So he will perform something called as a phase flip operation. Phase. So what is this phase? Ekadaina vinnari phase ana word ne. Right, I already mentioned in Bloch's P. What is this phase? The phi value. Phase is your phi value. Okay, a phi value on the chustara, we will call that phi value as phase. So rotation around z axis, of 45 degrees. Meaning is rotating with a phi of 45 degrees. Okay, meaning rotating with a phase of 45 degrees. I can say it in that way as well. Okay, phase is equal to phi. Simply consider like that. Okay, phase ante enti phi value. The phi value which I talked about when I was dealing with the Bloch sphere, when I was actually dealing with the Bloch sphere, I talked about phi value, right? This rotation on XY plane. So that guy is known as my phase. Okay, phase value. What is phase flip? Simple. If it is in positive direction, meaning if it is in on the X like this, for example, this is the Z. Okay, let us consider X is towards U. So if it is like this, let us consider. Now if I do a phase flip, what will happen? It will be like this. Meaning plus కాస్త minus అయిపోద్ది. Okay, this is plus X, right? This is plus Z and this is plus Y. So if it is in plus X, if I do phase flip, value will be same, but it will become minus. Okay, understood? So that is a phase flip. Meaning value will be same, but the angle will be minus. So దాన్ని one phase అంటాం. Meaning 0 is there. Okay. So don't consider Z gate, but normally I'm explaining the phase. 0 is there. So this will be here. Let us consider. Would not 0. Let us go with. Okay, let us consider super. Okay, not a problem. Let us consider some random state A. Okay. And if I do phase flip, it will become minus A. Okay, meaning opposite angle. Just consider it, simply consider it like an opposite angle. Okay, if it is positive, it will become negative. If it is negative, it will become positive. Just it will simply flip opposite ante. Value will not change. Value is A only, right? Value is A only, but only the sign changes. What is the definition of a vector? Vector has both magnitude and direction. So when I say minus 20 meter per second, what is the meaning behind it? Can the speed be in negative values? But is this value possible? It is possible. Minus 20 meter per second answer వస్తది. Okay. If the speed cannot be in negative values, how is this possible? Minus defines what? It defines the direction. It is not defining me the value, right? Same concept ikkada kuda. Okay. This minus defines what? It defines the direction. It defines the angle. ముందుందా వెనకాలందా పైన కింద అది చూపించేది నా sign. Okay, it is not defining me the value. What determining the value? This guy is determining my value. He is my value, not the angle. Got it? Sorry, got it? So that's a basic deal behind it. Understood? Now one more magic of Z gate. If the value is in zeroth state, it will not change the phase. Zeroth state on the value phase మారదు. Only one state on the value phase మారుతారు. Meaning I will show you. For example, let us consider I have my psi as alpha naught plus beta 1 ఉంది. Okay, this is my psi value, random psi value. Now for this psi value, if I am applying Z gate, okay, poly Z gate in a psi value apply చేస్తా, my output will look something like this. There is no change in my zeroth state. Zeroth state means change nahi hota. There won't be any change in zeroth state. But this guy is there na, he will become this. Okay, only my first state, I mean my 1th state sign flips. Okay, meaning the phase will be flipped only for the, what can I say, 1th state. Zeroth state may ఏమీ అవ్వదు. So nothing will be there in zeroth state. Got it? So that is your Z gate, phase flip operation. So I'll simply say Y gate. If you cannot understand, also not a problem. Don't break your heads for that. Okay. So there's something called as a Y gate as well, which is not that important at this point of time. Okay. So even if you can't understand, picture light, not a problem. It looks something like this: 0 minus I 0. Okay. So simply to put, why I said X and Z are important. Why I said like that, Ante? Why? Because of one simple thing. Y gate is there, right? Y gate is nothing but I X Z operation. Okay. Imaginary value into X gate into Z gate. That gives me Y gate. Okay. So Y is nothing, it's a combination of bit flip as well as angular flip. Sorry, phase flip. But it is nothing but the bit flip combined with phase flip with an imaginary touch is your Y gate. That's why it told not required at this point of time. At this point of time, really not required Y gate until or unless you are going way more deeper. That is 1 month or like let us consider 15 to 20 days into quantum. Then you require Y gate a lot. But at this point of time, for basic operations, you don't require Y gate. Okay. So even in the afternoon session, when you are dealing with the Dirichlet's algorithm or Grover's algorithm or even Shaw's algorithm, also you don't require Y gate that much. Okay, you only require XZ. That's it, and you have CXCZ. That one I will tell right. Okay, understood the concept. But Y is, if you anyone asks you the Y gate, simply say like Y is not a standalone gate. Y is a combination of imaginary value X and Z. So I linearly combine three of them. I mean, two gates I will combine one value. I will keep that value is imaginary value. It will be my Z gate. Sorry, Y gate. Okay, it is not a standalone gate. And what will Y do? It will combine bit flip along with the phase flip as well. Okay, change the flip phase with respect to bit. That is your Y. Simple. Not that required. Just keep it in your mind. So these are the three gates, three most important gates. What are they? Poly X matrix, which gives me X gate, poly Y matrix, which gives me Y gate, and poly Z matrix, which gives me Z gate. Okay, understood? Symbolically, plus this is Y only, and this is Z only. So this is a symbolic representation of these gates. Okay, X gate is determined by a plus with a circle. ఒక circle is a downloadable plus చేయండి. That will be X gate. Y is the same thing and Z is also the same thing. Not a problem. Same things. Okay. So this is my symbolic representation of my poly gates or the important gates. Now, so I will ask you a question. I hope you guys have written this one. Okay, for asking equal space only. X gate, Y gate. Sorry, X gate and Z. Forget Y. X gate and Z gate. Are they in superposition state or can they be in a normal state as well? Understand my question very well. Are they in a superposition state or can they be in a normal state as well? Like only zero state lo undocha, X gate and Z gate, or they should definitely be in a superposition state. And yeah, one more thing as a disclaimer, I mentioned you that every quantum state is in a superposition state, right? I'm not asking that question. Every quantum state is definitely in a superposition state. But my question is that can I get a value like this? Meaning nothing but alpha equal to 1 and beta equal to 0. So can I get a value like this when we are dealing with the, X gate and Z gate? Okay. Am I getting a value like this when dealing with X gate or Z gate? Yes or no? How many people say yes? Okay, the people who say no, why? Say why no. What will X gate do? X gate performs bit flip operation. I can give 0 and I will get 1. Is 1 is a linear combination of 0 and 1? Or is 1 is a standalone guy? 1 is a standalone guy only, kada. So I'm just getting like this. So Simply to put, your X gate and Z gate. I told you to forget Y, right? So just forget this guy off. Your X gate and Z gate, these two people can correspond to a single output. Okay, can correspond to a single output as well. Meaning it can correspond to a multi-qubit output as well. It can correspond to superposition state as well, not a problem. But a primary definition is a single one. Okay, single gate transformation, single state transformation. Now, if I wanna induce superposition, like for example, starting my has zeroth state to everything. If I wanna induce superposition into that, so meaning zeroth state ne, I wanna combine my zeroth state with the zero as well as one, thereby making it a superposition state. Are you guys getting the point? So initially, okay, I'll just mention it in a step-by-step manner. Normally, at the start of every quantum circuit, so how a quantum circuit looks like, and it will look something like this. So Q0, Q1, Q2. These are the number of qubits. Okay, so totally there are 3 qubits. Ani addam. Okay, Q0, Q1, and Q2. Okay, and when you are initializing a quantum circuit, the first state, the initialized state is always 0. Okay, the initialization, when you're initializing a qubit, the starting state will always be in a 0, not should, will. It will be in 0. Okay, so meaning they won't be in a superposition kind of thingy at the beginning of the circuit. When I create a quantum circuit, directly my qubits will not be in superposition. It will be in zeroth state. Now, in order to convert this single state into a superposition state, meaning right now I'm having a single value, I'm having only zeroth state, right? From that zeroth state, I want to convert it into a superposition state. At that time, what I will be doing? Simply, I will apply one gate, and that gate is called as Hadamard gate. Okay, so meaning a single state, meaning a zeroth state is a single state, one state is a single state. So a single state ni nenu superposition state loki marchali, meaning I want to convert a single state into a combination of states, meaning I want to convert a single guy into a superpositioned guy. For that I will be using something known as a Hadamard gate. Okay, so with by using this Hadamard gate, what I can do, single state ni combined state కింద మార్చొచ్చు అన్నమాట. ఓకేనా? So what will this Hadamard gate will do అంటే, it will look something like this. So Hadamard gate matrix goes like 1 by root 2 of 1 1 1 minus 1. So ఈ అసలు ఈ గేట్స్ అండ్ ఈ మ్యాట్రిసెస్ అన్ని ఏంటి I will say now. Like these are the responsibilities for your what can I say, final output. These are responsible for final output. How I will say it, listen. Now this is the Hadamard gate. Okay, now let me go back to the X gate. So what is the X gate matrix? 0 1 1 0. Okay, now I am asking you this one. So what is the answer for this one? I am asking, what is the answer for this one? What is the answer for this one? 1. Poly X on 0th state gives me 1. It's because I told you it's bit flip operation. Okay, let us consider you don't know it is bit flip operation, but you know only the matrices. Then how you can find? I already mentioned you. The logical gates are Boolean algebra. Okay, and the quantum gates are which algebra? Linear algebra, matrices. So if you do a matrix operations, you'll be getting the answer. Kada? So how I can get the answer? Simple. What is 0? What is 0th state? What is 0th state? 1 0. Just do this thing. What is poly X? This one. So 0 1 1 0 1 0. Calculate it. Matrix multiplication. Eighth class, ఎప్పుడు వస్తుంది? సరేలే మర్చిపోయా. So it will be 0 1. Okay, try to multiply it. The output will be 0 1. 0 1 is which state? 1 state. So that is how you get the answers. answer. Okay. Now, poly Z. Try to apply poly Z for the same zero one state. Try to apply a policy for one state, not zeroth state. Or do both of them. Try to do both of them as happy. So, what is poly matrix? Poly Z matrix? 1, 0. Raskunara? What is poly Z matrix? 1, 0, 0, minus 1. What is the output? I told you. What did I tell you? When you apply zeroth state for a poly Z matrix, there won't be any change, I told. Remember? Alpha naught plus beta 1, if you apply poly Z, you're getting alpha naught only. So not value. I mean the zeroth state will not change. Apply the same for the this gate, first state. Now see what is the output. Calculate what is the output. 0 and minus 1. So this is your one gate, one state, but with a negative sign. So this is how I am getting a phase flip only for my one state. Okay. So all are your matrix operations only. They are not the random rules which are created. All are my matrix operations only. Okay. So are you getting this? Why when you are applying poly Z, you are getting the you are flipping the phase only for the one state. It is because of this one. So just try to apply the matrix for the zeroth state. You got the zero only, no change. But try to apply it for a one state. You're getting the output as minus one, thereby making the phase flip. Understood? So that operation. Now try to apply Hadamard. Now try to apply Hadamard gate. So what is the Hadamard matrix? 1 by root 2 of 1, 1, 1 minus 1. So I can write it like 1 by root 2, 1 by root 2 minus 1 by root. Okay, now say what is the output? So what is this state? Get 0. Correct. Get 0 state. So meaning what operation I am doing? I am doing this operation. So what is the output? The output will be something called as Cesara. What is the values which you're getting? You'll be getting something like this actually. So I'll just derive like this. So you'll get something like yes or no. Are you guys getting this output? And 1 by root 2, 1 by root 2 chastare. You'll get the output like this. Okay. So you get the output like 1 by root 2 and 1 by root 2. It is nothing but 1 by root 2 common by is a 1 1. Okay. That 1 1, can I write this 1 1 as yes or no? Can I write this 1 1 in this way? Rayochan, because 1 1 ki state unda. Is there any state for this one? Is there any basis state for this one? No. So that's why it just decomposed into the basis states. Now what will happen? What is this 0 1? It is your ket 1. And this is my ket 0 plus. Meaning this output which I got. So I will write here. So when I apply a Hadamard gate for a 0th state, I got the output like this. Okay. Which is nothing but like this. Right. Which is nothing but right. So simply decomposing, which is nothing but got it. So meaning why did it went through all this stuff ante? Simple. Just think one thing. Whenever you are getting an answer, Just think one thing, after making it into ones and zeros only, okay? Don't think from here itself. Take out a common value outside. After taking a common value outside, it will become a binary state. It will only have ones and zeros, okay? Right now, it has only 1 and 1 at this step. Am I having any state or any base state like this? Do I have any base state for this 1, 1? Am I having any base state for this 1, 1? No, I do not have a base state for this 1, 1. Now you should be decomposing it into any number of matrices, which is a combination of the base states. Just keep that in your mind. Whenever you get a matrix, whenever you get an output, which is not a base state, if this output is not my base state, then what you should be doing simply, you should decompose that with as a linear combination of the base states. Okay, just simply decompose that as a linear combination of base states. So that's why I decompose this 1 1 as 1 0 plus 0 1. Why? 1 0 is my base state, ket 0. 0 1 is my base state, ket 1. I converted this as a linear combination of the base states. Linear combination is nothing but addition. Simple meaning. Addition or subtraction or ఏదో ఒకటి. Okay? And this is the output I got. So now, are you having a single state or are you having a combination of multiple states? What is the meaning behind that? It is in a superposition state. Got it? This is how your Hadamard gate is converting a single state to a superposition state by simply using this matrix sum operations. At the end of pointer. So how Hadamard converts a single state into a superposition? Simple matrices. By using the simple matrix, the pseudo multiplication, you get the answer over hyphen. And H with 0 gives me this guy, right? So Nandan Nilarastan actually. I can write it like this. Okay. And I will call this as plus state. Okay. I will call 0 plus 1 by 2 and get 0 plus get 1 divided by root 2. So I will call this value as plus state and antunded. Okay. Now try to apply Hadamard gate for your ket 1. If you try to apply Hadamard gate for your ket 1, do the same operations, you will get the output like this. You'll get an output in this way, actually. Okay? And you will call it as a minus state. Got it? Okay? These are random operations which you'll be doing. Conversion of a single gate to superposition state. Which gate you will use? If anyone asks you like that, what is the answer? Hadamard gate. Why Hadamard gate? Because it's matrix, if you do the linear algebra, you'll get a linear combination of the base states. Okay? The final answer or the final output after applying that matrix operations will be a linear combination of the base states. Whenever the output is a linear combination of base states, I will call it as a superposition state. Okay, just simply consider like that. And this is how you'll get it. H with naught, H with ket naught or ket 0 is called as plus state. Hadamard with ket 1, you'll get minus state. Minus will be there. Okay. So this is a simple deal which you need to remember. Done with this one. Got it? This particular operation, superposition state. Now. So how many gates we saw? X, Y, Z, H. Okay, we saw 4 gates. Now let's deal with the rotation gates. Okay. First, I will explain 2 by default rotation gates. Z gate, I will use it as a rotation gate. Yes or no? What will Z gate do? I told phase flip. Okay. What is phase? Phi. If I am rotating my state vector or if I am rotating my quantum state with respect to angle phi, what I am doing, I am rotating it with respect to which axis? Z axis. So simply to put, I am rotating it. Yes or no? So Z gate is called as or can be termed as a rotation gate. Okay. First thing, Z gate, I will write it like a phase flip. Second thing, I can consider Z gate as my rotation gate on z-axis only. Okay, the rotation gate on z-axis is my z-gate. My z-gate gives me the rotation on z-axis. Okay, that's the second deal of it. Rotation of which angle? Rotation of pi. Okay, minus అవుతుంది అంతే. So if it is 2 pi, it should be the same after a complete revolution. So it will become opposite. Meaning what it will happen? It will become pi. So Z gate is nothing but phase flip, which is nothing but rotation around Z axis with an angle of pi. Okay, that is Z gate. Now, irrespective of only pi, I can do the phase flip. I can do the phase flip of pi by 2 as well. Okay, meaning only 90 degrees. So this is achieved by something known as a S gate. Okay, S gate pair a S gate. Okay, by using S gate, what I can do? I can do the phase flip, not a complete phase flip. I can do the rotation around Z axis with an angle of 90 degrees. Rotation of 90 degrees around Z axis can be done by using S gate. Now, phase flip of pi by 4, 45 degrees. If I want to do the phase flip of 45 degrees, I will apply something called as a T gate. Okay, rotation around Z axis with an angle of 45 degrees can be achieved by using T gate. Okay, what is the matrices? S gate matrix will look something like this. T gate matrix will look something like. Okay, this is the S gate matrix and this is the T gate matrix. S gate matrix will look like 100 I. T gate matrix 100 e to the power of minus I pi by 4. Okay, now these are the matrices. Apply the matrices, you can see respective changes. That's up to you completely. But this is the main deal. Okay, so now if I ask you, what are the rotation gates? What you can say? Or by using which gates I can perform rotation? What you can say? Z gate, S gate, T gate. Can I call X gate as my rotation gate? Can I do that? Can I call X as my rotation gate? Yes or no? How many people say yes? Okay. Now, yes, I can do call that. I can call my X gate as a rotation gate as well. Why? Because see, what will X gate do? Bit flip. 0. So 0 state is in top. 1th state is where? It is in the bottom, south pole. So when I apply X gate, it is nothing but doing this operation. Yes or no? Meaning, is it flipping or not? It is doing the rotation, dude. It is doing rotation around which axis? X-axis only. It is doing a rotation around X-axis. That is your X gate. By default of, wait. Yeah. So I can consider X-axis as well, not a problem. So rotation of X-axis with an angle of pi, direct angle of pi. Okay, so I can call X as my rotation gate as well. Understood? Got it? So what are my rotation gates? Literally everything comes under a rotation gate, not a problem. But the typical rotation gates are ZST. ZST can be termed as a typical rotation gates, by default rotation gates. X is also a rotation only, but by default, if anyone asks you, just simply say Z and S and T. More than enough. Okay? Now, for example, I want flexibility, bro. If you are like, okay, Z is a flip of pi. S is a flip of 90 degrees. T is a flip of 45 degrees. That too only around Z axis. I want to flip around X axis with an angle of 20 degrees. How you can do it? For that also you have gates. Okay. If I want to randomly rotate my state, I don't want any static value. Right now, every gate we have seen are static values, right? Z gate is doing rotation around Z axis with an angle of pi, static value. T gate It is doing the rotation around z axis with an angle of pi by 2. Sorry, pi by 4. Yes, sir. With an angle of pi by 2. So all are static but not dynamic. I am not giving any value. Now let us consider if I want to give a value. I want to do the rotation with respect to x-axis. I want to rotate with respect to x-axis with an angle of 20 degrees. Okay. So I want to do the rotation with an angle of 20 degrees around x-axis. I don't have any gate for that. Now for static thingy. So for these dynamic values, I have three gates called as, the gates are itself known as Rx gate, Ry gate, and Rc gate. So gate pairla ivi. Okay, these are not formulas or something. The gates are itself this thing. Rx gate, Ry gate, and Rz gate or Rc gate. Okay, these are the direct gates. Okay, so why I will use Rx gate? Guess. If I want to rotate my state around x-axis for any random angle, that angle will be given by us. So that is the entire meaning behind it. So I want to rotate my state with respect to x-axis for 20 degrees. What I will be doing, I will simply, with respect to programming, I will write like this on mat. So 20 degrees convert it into pi by, so pi by 9, just do 3.14 by 9 actually. So I will do like this on mat. Okay, meaning what I am saying, so whenever I use this Rx, Ry, and Rz gate, there won't be any static angle. Okay, instead we should be the people, or we are responsible for providing this angle. Okay, we are responsible for providing by which angle I want to rotate my state. If I want to rotate my state with respect to x-axis for 20 degrees, I will be using this one. If I want to rotate my state with respect to y-axis for 45 degrees, what I will be doing, I should be writing here like this. Okay, why I wrote 0.700, the input value should be in radians. The input value should not be in degrees. So 45 degrees convert into radians, it will be something like 0.7053 or whatever. So that's the fun matter. Okay, so that is your Rx, Ry, and Rz gate. I want to rotate with respect to an axis with a by default angle of my own. I want to give any random angle. For that, I will be using these three gates. Okay, Rx, Ry, and Rz gate. Got it? So totally how many gates you have seen? First poly, Hadamard, two rotation gates, and three by default rotation gates. Okay, so you have covered all these gates right now. I hope you guys have written everything. So these are all the gates we have seen right now. These are all single qubit gates. So this all gates comes under something known as single qubit gates. So what do you mean by single qubit gates? And it's simple. To how many yeah, for how many qubits I am applying this operation? Am I applying it for multiple qubits, or am I applying for a single qubit? So how you can find out how many matrices I am doing the operation on? So I am doing my operation on only one of the row. Yes or no? So meaning it is a single qubit. Okay. So all these operations I am performing, I mean all these gates I am performing on single qubit only. That's why all these gates are called as single qubit gates. Okay. I hope you guys have written everything, right? So why we use T gate? ఒక్కళ్ళు గట్టిగా ఏం అక్కర్లే అట్లీస్ట్ ఒక్కళ్ళు నార్మల్ నోట్ తెచ్చి చెప్పినా కూడా నాకు అర్థం అవుతారు యాక్చువల్లీ కరెక్ట్ యా z axis 45 degrees t simple deal. Why we use Rx, Ry, and Rz? To rotate based on our own axis with our own angle. For that we will be using RZ, R gates. So R gates do have a particular matrix representation, but the better representation for R gates looks something like this. So if I want to go like Rn, okay, with an angle theta, this is represented in this format. like e to the power of minus sigma n of theta. Yeah. Here we will be having some r, I guess. So this is how it looks like. So this is the operation. For example, if I say rotation around x-axis with an angle of 3.14 radians, meaning pi, it is a random, sorry, it is an operation of sigma x, meaning here we will be having, what is the sigma x determine? Poly, poly x matrix. Poly x matrix, a complete matrix, a single entity, ka, single value, ka, that's a complete matrix of 3.1. Okay, so this is the formula anamata to convert. We do have a matrix, but the best representation is this one. Okay, instead of directly doing the entire matrix, the best representation for rotation gates is this one, this formula. Okay, some r naught, which is greater than or equal to 0, e to the power of minus sigma n of theta. Okay, I minus I, sigma n of theta. Okay, so there we have an imaginary guy as well. So this is how this looks like. This is the rotation formula. These are the rotation gates. Now let's go to multi-qubit gates. Multi-qubit gates are very easy, very straightforward. So how you can convert a single gate into a multi-qubit gate? Simple. Keep a word called control behind, in front of it. It will become a multi-qubit gate. Okay. Or most likely to say double qubit or two qubit gates. What do you mean by this control thing is, first of all? Okay, so first of all, I would like to show you a random circuit, how it actually looks like. I'll just draw it. So Q naught, Q1. For example, if I want to take two qubits, I will write like this, Anmata. So what is the initial state of these two? 0, catch 0. So Q naught is catch 0 and Q1 is catch 0. Okay. Now, if I want to convert Q naught to 1, what I will do? X, good. So I'll simply keep a X gate here. Okay. After keeping an X gate, I want to do the superposition. At the time, what I will need to keep? I should keep a Hadamard gate. Okay. So afterwards, what I want to do, ante, I want to convert this guy into my 1 as well. So at the time, I will be doing something called as X gate here, thereby converting this into 1. And then I should flip it. I should make it -1. At the time, what I should be doing? Which gate? Z gate. Okay. So this is how the circuit looks like casually if I want to apply the operation. This is not any circuit, a random circuit which I'm just simply saying, but this is how it looks like and this is how the operation goes. Operation goes from left to right only. Okay. Operation goes from left to right only. Sarana, don't confuse from right to left matrix thing. No. That is only for pen and paper. Like if you want to calculate or if you want to write it in a formula point of view, at that time only you should follow that right to left convention. In remaining all cases, it is left to right only. Okay, so the game starts in this way only. Sarana, now, now I would like to tell you about two things actually with respect to a circuit. There will be actually three things. First thing is known as my qubit. Okay, so how many qubits are there here? Two qubits. That is the number of qubits. So after looking at a circuit, you should definitely say four things actually. First thing is number of qubits. Second thing is number of classical bits. Third thing is something known as the depth of the circuit. And fourth thing is known as the length of the circuit. Okay. You should remember 4 points whenever you see circuit. Okay. And you need to tell them, like if anyone asks you. First thing, the number of qubits. So how many qubits are there here? Two qubits. So the number of qubits is 2. Second thing is number of classical bits. So how I will be defining a classical bit ante? So after the qubits are done with a single line, below the all the qubits, you can see something like this. You'll see something like this. Okay, this indicates the presence of a classical bit. it will not show you the number of classical bits. It indicates the presence of a classical bit. Okay, so there is a classical bit. So how I can find how many classical bits are there? Typically in a quantum circuit, the number of values I am measuring is corresponds to the number of classical bits which I want. Okay, the number of qubits I want to measure corresponds to the number of classical bits I want to have. Okay, simple. For example, in this circuit, I want to measure only Q1. I want to measure only Q1, meaning the second qubit. I want to measure only the second qubit, meaning how many classical bits I need to have? Only one classical bit. Why? Because I want to measure only one qubit gravity. So how I can show the measurement under simple. So there will be something like this actually. Keep a box and keep like a speedometer symbol. So you can see in bikes and all, there will be the speedometer, right? 10, 20, 30, 40 kmph. That speedometer symbol will be there. Na? That speedometer symbol is the measurement gate symbol. Okay. So if you're seeing a measurement, if you're seeing like something like a speedometer inside a circuit, meaning its measurement is being done. And you'll see something like this. So there will be a line from that speedometer symbol to this straight line, meaning I'm considering that, and here it will be 0. Meaning my 0th classical bit is holding the value of Q1. So I measure the qubit Q1. It obviously decomposes into one of the base state, and that one of the base state is being stored in the classical bit called 0 ani artham. So how many classical bits are there here? 1. Okay. So now if I want to measure Q0 as well, then what I will be doing? Draw the same thing for that as well. Simple. So I will just keep a box, draw a speedometer, keep a straight line, make it 1. Okay, that's it. Whenever you keep a speedometer symbol, meaning is measurement. I am doing a measurement on it. That's it. And when you keep a straight line touching this guy, the double layered line, meaning that value is being stored in the classical bit. Aniyad. So the meaning behind this is the Q naught value is stored in first classical bit, and the Q1 value is stored in 0th classical bit. Understood the diagram, everyone? Did you guys get the circuit? అర్థమైందా? Like how the measurement is being done అని చెప్పి. Okay. Now, third thing, depth of the circuit. What do you mean by circuit depth? Simply, what you need to consider ante, look at the line. Okay, there will be a very big definition of the depth, but in order to consider simply, look at the level actually. Now, X gate and X gate. These two can execute at the same time, yes or no? Is there any relation between these two gates? I mean, these two qubits at this point of time? ఏమైనా కనెక్షన్ ఉందా? లేదు. అంటే this operation as well as this operation, both of them can execute parallelly, right? So this is level 1. Same here. Hadamard and Qiskit. Can they execute parallelly, or is there any connection between them? There is no connection. So they can execute parallelly at the same time. This comes under level 2. So the depth of the circuit is 2. Okay. The number of operations which can execute parallelly at the same time, simultaneously, if they can execute, then I will call it as a 1 level. Okay. Simple. Fourth one, length. Number of gates you are using is known as the length of the circuit. Okay. How many gates you are using in this circuit? Don't consider measurement. Measurement is not a gate. It's a value. It's a normal operation. And the measurement gate card. How many gates I am using here? 4 gates. X, X, H, Z. And okay, so yeah, that's actually correct. But the point is 4 gates ane లెక్క వస్తది అన్నమాట. So identical gate నేను multiple times use చేస్తున్నాను. It's a gate only. I am applying that operation అనే అర్థం. So I am applying the operation 4 times. 4 operations I am applying. Even though same operation I am repeating it twice, but I am doing the calculation 4 times. So that's why the length is 4. Okay. This is known as a circuit length. Okay. So if I'm able to execute parallelly, that is considered as one level. So you can see the difference between depth and length, right? Okay, length meaning is how many operations? One, two, three, four. Four operations. Depth meaning is how many parallel operations. First two things can execute parallelly. Second two things can execute parallelly. So totally two parallel operations only which is happening. So that is my depth. Or I can say independent operations. That's it. Okay, that is my circuit depth. So you need to remember these four things whenever you see a circuit. Okay, and measurement also remember it very well. Now, yeah. Now let's go with multi-qubit gates. Very easy actually. Multi-qubit gates are so easy. It's nothing but a combination of single qubit gate with something called as a control. Ante. ఏమవుతుందంటే C. Q not a Q1 కదా. Okay. X. This is a plus symbol. Okay. Okay. Now, so the meaning behind this is, let us go with our first multi-qubit gate or two qubit gate, which is known as C naught gate. The first two qubit gate, which is known as a C naught gate. So what will a C naught gate will do ante every time C naught ki meaning entante controlled naught gate. The meaning of C goes like controlled. So it is not but controlled naught gate. What is a naught gate in quantum? X gate. So that's why symbolic representation is this one. Symbolic representation is something like this. And letter wise representation is this one. CX. So CX is the representation of controlled NOT gate and symbol is this one. Okay. So what is the meaning behind this thing? This dot is there, na? This dot is something called as control. Okay. And this plus is a X gate. Plus man X gate symbol kar guttonda. This will be on something called as a target. Okay. So what is the meaning behind this? Very simple. Meaning behind this goes like, for example, I do this now, I did this, right? So can you see the circuit? So what is happening here? First two qubit initialization, I created two qubits. For the first qubit, I applied X gate. Meaning what happened here, it is zeroth state, zeroth state. Okay. Now here it will be what state? It will become 1. So here it is 1. Here 0 only. Right? No change. Why? Because I did not do any here, till here. I did not apply any change, right? Till here. I just applied a change on qubit 0. That is the first qubit. I applied only an X gate on first qubit. So initially it is in 0th state. And after applying the first qubit change of X gate, then my first qubit changed into 1th state. But my second qubit is still the same because I did not use any operation. What is the meaning of this C symbol? Okay, just try, don't go like controlled X gate. I mean, don't go like C naught gate, but I'm telling the meaning of C. What is the meaning of control ante? Simple. I am saying like this defines that if if control is 1, if control is 1, then apply X on target. So that is the meaning behind a controlled gate. Okay, so this is the meaning behind your CX gate. Meaning controlled X gate is nothing but C naught gate. Okay, so what is the meaning of this controlled X gate? And it's simple. This X operation is being controlled by this controlled qubit. Meaning, when I do this, what is this dot defines the control and this plus defines the target. So the meaning goes like this. If the controlled value and if the control qubit value is 1, then only apply the X gate for my target. That is the meaning behind it. Okay, if control is 1, then only apply the X gate to my target. So now what will be the state here for this guy? For Q naught, what will be the state here at this point? 1 only, no change, same only. Why? Because I did not apply any change. For this gate, it will be 1. Why it changed to 1? Exactly. Why? Because the control value is 1. As the control value is 1, it will perform the X gate. Okay. So this is known as the controlled X gate or controlled NOT gate. If the control is 1, then only the target will apply that particular change. What do you mean by controlled Z gate? Then CZ gate will be there. Controlled Z gate. Ante enti? Exactly. If the control is 1, then apply the Z gate transformation, meaning then apply the phase flip for my target. That is the meaning behind controlled Z gate. Adhavenda controlled Z gate ki meaning enti? If the control value is 1, then apply the Z gate for the target. That is the meaning behind it. Okay. So controlled Z gate symbol is this actually. రెండు మీకు డాట్ లో ఉంటాయి. సో అందుకే ఇన్వర్స్ లో మనం చెయ్యలేము అనమాట కంట్రోల్ సి గేట్ ని. అంటే చెయ్యొచ్చు బట్ మనకు అర్థం కాదు. దట్స్ సింపుల్. బికాస్ కంట్రోల్ సి గేట్ హ్యాస్ 2 డాట్స్. సో కంట్రోల్ విల్ బి a dot and target will also be a dot. So circuit mein you can't understand what is what. That's why in code you can understand. Obviously మనమే రాస్తాం కాబట్టి ప్రాబ్లం లేదు. బట్ అదేంటి లైక్ ఇన్ circuit you can't understand because both of them will be a dots. This typically this is control and this is target. And here we have a clear cut definition. Dot is a control, plus is a target. Now, if you want to see the matrix, the CX matrix will look something like this. Normally, if you have a single qubit gate, the matrix will be 2 cross 2. Okay, ఎందుకంటే రెండు స్టేట్ లో ఉన్నాయి కదా 0 and 1. Okay, but if when you're dealing with a 2 qubit gate, the matrix size will be 4 cross 4. Why? Because how many states we have? We can have 2 to the power of n. Right? So 2 square. Total you can have 4 possible states. 0, 0, 0, 1, 1, 0, 1, 1 annan kada. So you can have all those possible values. And if you're having only a single qubit, the output is only 0 or 1. So that's why it's only 2. Okay? So it will look something like this. 1, 1. So this is a C naught gate. Okay? 1 ఇక్కడ మాత్రం flip ఉంటుంది. CZ gate. This also have 4. This is also a 4 cross 4 matrix. Why? 2 qubit gate. Total number of possible states is 4. That's it. This is a CC gate. Okay? Controlled set gate ani అర్థం. సరేనా? Understood? So these two are the most widely used 2 qubit gates. Done with this one? Can we go with entanglement or can I stop? Okay. We can continue till 5. ఒక రౌండ్ ఫిగర్ లో ఆపితే బాగుంటది కదా అర్ధదిద్దంగా ఆపితే దరిద్రంగా ఉంటుంది so there's only 10 minutes of time so not a problem but did you guys understood the 2 qubit gate yeah okay so did you guys understood 2 qubit gate single qubit and 2 qubit how a circuit looks like classical bits ఎలా ఉంటది qubits ఎలా ఉంటది measurement gate ఎలా ఉంటది అన్ని తెలిసిపోయినాయి కదా all cool Let's go with entanglement. Entanglement is a very good concept actually. It's better. I like entanglement more than superposition. So, what is entanglement? Very simple. Heavy correlation. Okay. If two qubits, okay, entanglement only resides on multi-qubit. Single qubit entanglement లో ఉండవు. Superposition single qubit లో కూడా ఉండొచ్చు. బట్ ఎంటాంగిల్మెంట్ అనేది పక్కా మీకు మల్టీ క్యూబిట్ ఉండాలి. మోర్ దెన్ 1 క్యూబిట్ ఉంటేనే ఎంటాంగిల్. ఓకే. సో డెఫినెట్లీ యూ షుడ్ హ్యావ్ మోర్ దెన్ 1 క్యూబిట్ ఫర్ ఎంటాంగిల్మెంట్ టు హ్యాపెన్. What is entanglement? I can say entanglement as heavy relation. Meaning, so I will directly say with the definition, directly say with the properties. There is no need of a proper definition. Properties చెప్పేస్తే మీకే అర్థమైపోద్ది. First, I will ask you a question. What is the fastest thing in this earth? Ah, nice. Speed anta? Nice. Right? అక్కడే ఉండండి. Like fix on that one point, I will say. So, before actually going into entanglement, we need to know about two terms. One is known as locality and realism. Okay, these two terms are very key. Okay, first thing, locality, meaning is simply to put, there can be multiple things, but I will directly say the only thing which is necessary. When two channels are passing information, the speed, or I can say the time for for the information to reach from one channel to another channel. Ante from A to B anukundam. From A to B depends on the distance between A and B. Can I keep it in this way? So how many of you agree for this fact? Then okay, information pass cheyali. Like I'm here and the person who I want to convey the information is at a particular distance x from me. So the time at which the information goes to that guy depends on the distance between us. How many of you accept for this fact? Accept. Nice. And okay, all accept. Why accept? Accept. Okay, but why accept? Why are you guys accepting the fact that it depends on the distance? Correct, correct. I think you were mentioning correct word. It depends on the light actually. Okay, so the speed at which the information travels is equal to the speed of light. Okay, so light on a speed ante mari anta light undale gaani approximately equal to light speed lo information travel avutadi. Let us consider I am here. My friend is here only on earth. Let us consider my friend is on earth, then it is approximately the same everywhere. But if let us consider my friend is something like in Andromeda galaxy, which is something like the hundreds of thousands of light years away from Earth. I don't remember the perfect value. So it will take hundreds of thousands of years for him to receive my information, which I'm telling him right now, right? So you might have heard this particular thing. So you might have heard, like for example, if an alien is there somewhere, and if that alien looks at a telescope to the Earth, it will see dinosaurs, but it will not see us. I hope you guys have heard this one somewhere, right? So where, why? Sorry, not where. Why? Why? Because the light of dinosaurs is still traveling in space somewhere. Okay, and then when they are seeing that light of dinosaurs which is traveling from at that time will reach them. Okay, because it is that far covered. That is a logic behind it, and that's how the information and light will travel actually. ఓకే. మనందరూ ఎర్త్‌లోనే ఉన్నాం కాబట్టి తేడా తెలియట్లే గానీ, ఫర్ ఎగ్జాంపుల్ ఇఫ్ let us consider my friend is an Andromeda, as I already mentioned, then there will be a huge difference actually. So if I tell him something, tell him anything at this point of time, he will receive after hundreds of thousands of light years. Okay. So why? Because we are that much far from each other. So that's why the information depends on the distance. That is locality. Second, realism. Independent. Okay. Independent kind irrespective. Irrespective of the I can simply say like combined measurement, combined or joint measurement, individual elements or individual I can say qubits or properties or whatever, individual items, simply to put, individual entities perform their individual behavior, or I can say their identical behavior. Meaning, for example, I have two bottles, let us consider. One bottle I'm having it me, one bottle I give you. And sorry, two bottles are there, one bottle I'm giving it to you, and one more bottle I'm giving it to your friend. And I'm telling both of them to start drinking. Is your drinking affects your friend's drinking? No. Right? So it's not some joint competition, right? So you are drinking, he is drinking. So there's no relation between them. So both are identical concepts, or both are irrespective individual concepts. So there's no direct relation between them. So that is known as realism. Okay, meaning each individual entity will perform its own action, irrespective of the peers or irrespective of the groupings or irrespective of the couplings. Each individual entity or each individual material has its own properties or has its own stuff, irrespective of anything. Okay, so that is realism. So these two make sense, yes or no? And these two are the facts of the world, right? So that's how the everything works. Locality, that's how it works. Why? Because the fastest travel is light. So light years అవుతుంది దానికన్నా తక్కువ అవదు. So locality works. Realism also works. So if I want to measure something, I am measuring that thing only based on that particular properties. And if I want to measure this plant or something of this plant, let us consider I want to measure the chemical composition of this soil. It does not depend on some random chemical composition in Toronto or USA, right? So it is this thing only. So it depends on this one only. Okay. And as well as doesn't depend on the random soil outside the campus itself, where we are doing some pesticides. So where we gave, so like where we are um, throwing some pesticides on the soil outside the campus, that thing also doesn't influence this measurement, right? This chemical composition is this one only. Okay, there's no change between there is no dependent from this with the actual soil outside. So both are identical in nature. Okay, until unless I go and mix them, both are identical in nature. It doesn't depend on anything. So these two make sense, right? Your entanglement breaks these two things. Your entanglement breaks the property of locality and breaks the property of realism as well. Okay, so how it is breaking the property of these two? And I don't want to exaggerate it because it's already fine. Simply to put, so there will be relation in such a heavy manner that if I and my friend has entangled qubits and we are depending on the quantum channel for communication rather than the classical telephone or something, if I say him hi at this point of time, at this time itself, he's even though he's in Andromeda galaxy, he will get my message. Okay, it thereby breaking the locality principle. Even though he's in Andromeda, even though he's in some random XYZ which is of hundreds of thousands of light years away from me, at this point of time, if I say hi, he'll get the information right now itself. He don't need to wait for that light year number of years in order to get the information. So thereby breaking the locality. Now, how the realism is breaking ante, so no one knows whether the realism is breaking or not. That's actually still in research. The point is, if the locality need to break, locality is already broken. Okay, locality is officially broken, so that won't be a problem. For realism, why they're considering like realism will not work until if your locality should not work. Like for locality not working, realism should not be there. If the realism is there, then a locality will also be preserved actually. So if the realism is preserved, then a locality is preserved. But the locality is broke, right? So thereby scientists are considering that the realism is also be or also can be broken or something like that. Okay. Thereby your entanglement is nothing but such a heavy correlation between the qubits that the measurement of one qubit, like there are two qubits ankundam. So if I entangle two qubits very heavily, like normally we will entangle them in a very low temperatures anamata minus 300 degrees Celsius mein. If you keep two qubits na, sorry, if you keep two subatomic particles, normally like charges repel each other, right? Minus minus will repel each other. But if you're keeping in a very cool temperature, they will become opposite. Like charges will attract and unlike charges will repel in a very cool temperatures minus 300 degrees Celsius or something like that. Okay. So because of that phenomenon, what will happen? And these two subatomic particles will be very heavily correlated. Okay, they will they will attract and they will become very heavily correlated in such a way that they will be entangled somehow. Okay, and after getting entangled, if I split them, and if I have one subatomic particle with me, and if I give you one subatomic particle, and if I tell you to go to Andromeda galaxy, and you went to Andromeda galaxy somehow, okay, you are like hundreds of thousands of light years away from me at this point of time. Now, if I measure my qubit here, and my qubit gave the output as some random value, some value came 1 or 0, ఏదో ఒక value వచ్చింది. Now, automatically, your qubit in the Andromeda galaxy will also give even the same answer or the different answer based on the entanglement which will happen. So, for this case, let us consider different answer. So, if I got the answer as 0 when I'm measuring my qubit, then automatically your answer is 1. You don't need to measure as well. Your answer is 1 only. Point goes like how the information that my answer is 0 is getting like is traveling to you, and it is traveling to your qubit even though you're that many light years far from me. That is the question actually, and we don't know the answer for that till now. Okay, so that is the actual question. So meaning you are so many light years far away from me, I measure my qubit, it gave me the answer as 0. Okay, then your qubit will automatically be 1. Let us consider I am entangling it in that way. There are totally 4 states. Let us consider one of the state lo opposite వస్తది, two states lo opposite వస్తది, one state lo same వస్తది అన్నమాట. Let us consider we are considering the opposite state. So if I measure 0 here, instantly your qubit will be 1. Okay, how the information is traveling from me to you, who you are like some hundreds of thousands of light years away from me, that is a question, and that is known as entanglement actually. So they're such heavily correlated that the measurement on one qubit is reflected on the measurement of other qubit even though it is so much far away or whatever it is. So that is known as entanglement theory, and this is heavily useful when you're dealing with communications and stuff. How scientists found that locality is broken and how the realism is broken and what are the applications. So we can do the teleportation by using this entanglement theory only. Okay. So quantum teleportation cheyochu, like how communication is possible. So all these things we can see in tomorrow's session. Okay. Why? Because it's already 5 and I don't want to bore you more about it. Cool. Done. Everyone. Thank you. So if you're having any queries, you can ask me right now. Leva. Thank you. Okay. So if you're having doubts, you can ask me actually.
Good evening, sir.
Good evening,
So,
ma'am.
firstly, a heartfelt thank you to giving this workshop, sir. Because on behalf of all the students, I am representing a heartfelt thanks. Because before attending this session, I was confused about where to start. Firstly, after attending this session, I just got clarity. So, what is what on basics? So, my question is a basic question. Could you please tell us what is the roadmap to and where do we start to explore these quantum worlds?
Okay, so that's
as a
actually,
beginner.
yeah, okay, cool, cool. Thank you for asking me that. Actually, we made a roadmap by combining with Nikhil and Kasim. We prepared the roadmap. We'll be providing you by tomorrow, actually. So tomorrow also we are having a session. So by the end of tomorrow session, we will be definitely providing you everything clearly.
Okay, sir.
Okay.
And one more thing, sir. So by using this quantum computing, we can do possible, which are impossible things, right, sir? Impossible things can be possible by using this quantum computing.
Okay, approximately.
Yeah. So can we find exact treatment for cancer, sir? Like
Yes. Actually, the treatment for cancer depends on the drug directly.
yes,
So
sir.
it is not some random operation, right? So that can be achieved by using the drug discovery optimization.
Yes,
So
sir.
we can do the drug discovery optimization actually. So there's a company in Hyderabad, which is the company who I know very well. So they are practicing on this thing only. So we are providing them a quantum solution. Maybe that can be achievable for that.
Okay, sir. Thank you.
Thank you so much. Okay, so I hope there are no further queries. Are there any further queries?
Seems like there are no more queries, sir.
Okay, cool. Thank you so much, guys.
Thank you so much, sir. Thank you for such an insightful session. Not just today, but all the sessions you have taken so far, they're really inspirational. I've just gone through the feedback of so many students also. It's really awesome, sir. We didn't even expect that high level of feedback from the students. And the pin drop silence and focus of all our attendees to the workshop session today and their active responses, and somehow the feedback and questions of the attendees is also a simple and clear acknowledgement of how awesome your session was. We sincerely thank you for sharing your knowledge and guiding us through today's session and contributing to an enriching learning experience at Qiskit Fall Fest 2025, sir. Thank you so much, sir. And guys, show how much we love the workshop session with the sound of our applause buddies. So all the attendees, dear participants, whoever are here and whoever are watching this session online, please scan the QR code and confirm your attendance and also provide your valuable feedback. That means a lot to all of us. In the meanwhile, while you are filling that form, there is a little exciting announcement. You know, we'll be conducting a hackathon, a 48-hour continuous hackathon as a part of this fest, right? We have reached 100 plus teams of registrations for hackathons today. And by tomorrow afternoon, the Joint Collector of Srikakulam will be inaugurating the hackathon session. To all the participants, thanks a lot. Thank you so much for your patience and your everlasting enthusiasm to learn and to grow and to contribute to the nation. Thank you, guys. After filling this form, you can wind.